Another application of equilibrium that we can explore is the role that equilibrium plays in terms of solubility. Now, we've talked about some things being insoluble and some things being soluble. Really, the things that are insoluble are still very slightly soluble. A small amount of that solid dissociates in solution, dissociates in water, but most of it stays together. So if we look at it from an equilibrium standpoint, we can talk about something called the solubility product, or KSP. Now, just a reminder, solubility is a measure of how much of a solid will dissolve into the liquid. And usually we're talking about ionic things dissolving in water. Not always exclusively, but for our purposes, those are the examples I'm going to use. Right? So it's a measure of the amount, either the grams or moles, that dissolve per liter. So we can talk about something called the solubility product, and it's called a product because the only parts of the expression that are here are multipliers. There's no denominator in this fraction, as you'll see. So if we look at something like calcium fluoride, fluorides are rather insoluble. A small amount of that calcium will dissociate into Ca+2 ions and 2 F- ions. And when it dissociates, that's the part that goes into solution. Most of it stays together, because the product, the KSP, which would be a function of the two aqueous components and not the solid, that's why there's no denominator, there's no reactant here that fits into an equilibrium expression. The product of those concentrations always has to be 4.0 times 10 to the negative 8th. Okay? And that would be the equilibrium expression here, because I get 2 fluoride ions for every 1 calcium. So if I were to try to solve for particular concentrations, I could figure out how much of each goes in given the KSP value. So this would be x, this would be 2x, and then squared, and I do the algebra and I solve for the answer. So we can look at how soluble something is by looking at its solubility product. And again, the more negative, negative the exponent on the 10 is, the less soluble it is, the less actually becomes ions. Okay, so these are really small K values. Now, the other thing we have to consider is something called the common ion effect. If I'm going to dissolve something, or if I'm going to combine two solutions, and they both share a common ion, the substance that is less soluble will be even less soluble, will have a lower solubility than what its KSP would predict, because of the presence of the common ion, or the shared ion. So plugging it into the KSP expression, if we were to solve for how much of the other ion actually goes into solution, would be even lower than if we dissolved it in pure water. So if we're adding an ionic compound, like say silver chloride, and if we were to add it to a sodium chloride solution, this is why silver nitrate is a good indicator for chloride ions, because it's so insoluble. Look, the KSP value in pure water is 1.8 times 10 to the negative 10. Sorry, and the expression would be the concentration of the Ag ions and the concentration of the Cl ions, because it's a 1-to-1 ratio. So if there's extra Cl ions, chloride ions, because we have a sodium chloride solution that we're adding this to, the amount of silver that actually goes into solution is even less. Already it was going to be a tiny amount, now it's suppressed more. This concept is also very relevant when we talk about weak acids and weak bases. What makes something a weak acid or a weak base is that only part of it dissociates. Like, so for weak acids, the hydrogen, the acid hydrogen, only a small percentage of the compound, of the molecules that have the acid hydrogen actually dissociate and donate the acid hydrogen. And the other part is the conjugate base. If we add a weak acid to a solution that also has the salt, which produces its conjugate base, then that even reduces the amount of acid hydrogens that are released. So the pH is actually higher than it would be if we had a pure solution of that weak acid. That, of course, is a discussion for another video, but the common ion effect is something that has impact in solubility and also weak acid and weak base equilibrium.